So, good morning, students. Last time you have learned the introductory part of the thermodynamics, and all of you know a spontaneous processes, the process which takes place on its own accord, and in nature, the spontaneous processes they occurs without addition of any external agency. In this picture, this is not a spontaneous process. Okay, then here it is a system. Out of this is surrounding, and to find the total entropy of this system, here total entropy change of this system, it is the entropy of system plus entropy of surrounding, and it is always greater than 0. And every time it is not possible to say that or to measure the entropy of system and entropy of surrounding. Okay, here the total entropy of any system, it is the entropy of system plus entropy of surrounding, and it is not possible every time to measure the entropy of system and surrounding. And in the second law of thermodynamics, you have learned entropy. It is a criteria of a spontaneous process. That means each and every spontaneous process takes place with increase in entropy. So, to overcome this problem, the scientist Gibbs he introduced a new function in the thermodynamics, and the Gibbs free energy. That function, it is the Gibbs free energy. It is denoted by letter G, and Gibbs free energy, it is the measure of maximum amount of energy available to a system during a process for doing useful work under constant temperature and pressure. Remember that the Gibbs free energy, it is the energy available to a system during a process for doing useful work under constant temperature and pressure, and it is denoted by letter G. Then all of you know the process which is carried out at constant pressure and temperature, its total energy, it is the enthalpy of the system. It is denoted by letter H, and this minus Ts, and it is the product of temperature and entropy of the system. That means the total enthalpy or total energy content of the system H, it is equal to G plus Ts. G plus Ts, where this G is the energy available to do a useful work, and the remaining energy which is wasted in doing unuseful work, that is unavailable energy for doing work, it is given by the product of temperature and entropy. So we have, this is the mathematical expression for the Gibbs free energy. G, it is equal to H minus Ts, where G, it is the energy which is utilized in the in doing useful work, while this Ts, the product of temperature and entropy, it gives the energy which is unavailable to do the work. Then the small change in the Gibbs energy for infinitesimally small process or small change, it is given by dg, and it is equal to dh minus t ds, where T, it is a constant. That means for isothermal process, this equation it becomes as dg, it is equal to dH minus T ds. And for finite change, this equation we can write delta G, it is equal to delta H minus T delta S, where delta G it is equal to G2 minus G1, delta H it is equal to H2 minus H1, and delta S it is the S2 minus S1, and we kept this temperature a constant. Okay, this is the change in Gibbs free energy for a finite process or finite change, and small change we can denote by letter small d, dg it is equal to dh minus t ds. Then the next term, that is the Helmholtz free energy. Again, the Helmholtz free energy, it is also a energy available to do a useful work. And the Helmholtz free energy is a thermodynamic potential that measures the useful work obtainable from a closed thermodynamic system at constant temperature and volume. Remember here, the Helmholtz he carried out reactions at constant temperature and constant volume, while Gibbs carried out the reactions at constant temperature and pressure. And the Helmholtz energy is mathematically defined as A. It is the notation of Helmholtz free energy. It is also called as work function. A, it is equal to U minus Ts. E minus Ts, where A, it is the Helmholtz free energy. U, it is the notation for internal energy. As usual, T, it is the absolute temperature. S, it is the entropy. Okay, this A, it is the Helmholtz free energy, and its SI unit is a joules and CGS unit it is a earth. You in your book, your textbook, the internal energy it is denoted by letter capital E, and here it is denoted by U, and it has also unit joules and CGS unit earth, and T is the absolute temperature. T is a absolute temperature, and it is expressed in Kelvin. S is a entropy. It's a unit joules per Kelvin. दीदी मैं पैसे दे रहा हूँ. Yes, it is a entropy joules per Kelvin, and its CGS unit earth per Kelvin. Then the physical significance of Gibbs free energy. At constant temperature Tg, we have an infinitesimally small change in the Gibbs free energy. We have dg it is equal to dh minus tds, and again we have h, that is enthalpy, it is equal to u plus pv. And differentiating this equation and putting the value of dh, we can have this equation dg it is equal to du plus pdv plus pdp minus tds, it is equal to dq minus dw plus pdp plus pdp minus tds. And from the definition of entropy change, dq it is equal dq by t it is the ds, therefore tds it will replace by dq, and subtracting these two terms, we can have dg it is equal to dw plus pd phi plus pdp. Now, considering that the total work is sum of expansion work and other type of work, that is the mechanical work. Therefore, we can write dw it is equal to minus pdp minus the mechanical work. At, as a result, at constant pressure, we finally obtain dg it is equal to W maximum, and the significance of this equation, that is the Gibbs free energy change, represents the maximum available work or the useful work that we can obtain from a given process. Then see here the some points here we can see. Okay, the concept of Gibbs free energy and Helmholtz free energy. This Gibbs free energy function it was introduced by the scientist J. Willard Gibbs to account for the work of expansion due to volume change in chemical process, while explaining the concept of maximum work. Gibbs free energy it is introduced by the scientist J. Willard Gibbs to account for the work of expansion due to volume change in a chemical process, while explaining the concept of maximum work. It is represented by symbol G, and mathematically it is expressed as G it is equal to H minus Ts, where H it is the enthalpy or total energy of the system which is carried out at constant temperature and pressure, and G it is the energy which is utilized in doing useful work, and this is the energy which is utilized in doing unuseful work. So the total energy it is the sum of energy utilized in doing useful work plus energy used in doing unuseful work. So that we have this equation G it is equal to H minus Ts, and it is a state function because the enthalpy H, entropy S and temperature, these are all state functions. They depends only on initial state and final state. Its absolute value we cannot determine or we cannot find out. We can find only the change in the state functions. Then it is also defined as the energy available to do useful work. Then the next characteristic point here, it is a property that provides a convenient measure of driving force of a reaction. When a system changes from one state to another, the net available energy under specified conditions results from a decrease in Gibbs free energy. For every spontaneous change, the Gibbs free energy it decreases. Then the Gibbs free energy change delta G is related to enthalpy change delta H and entropy change delta S by the relation here delta G it is equal to delta H minus T delta S. For isothermal process we kept constant temperature, so that we can write the change in Gibbs free energy delta G for isothermal process as delta G it is equal to delta H minus T delta S, where delta G means G2 minus G1, delta H H2 minus H1, and delta S S2 minus S1. That is the free energy, enthalpy, and entropy. All these are state functions. Then, for a spontaneous chemical reaction to occur, delta G must be negative. That means delta G decreases as process is uh, delta G decreases for any spontaneous process. Then, for a chemical reaction at equilibrium, the equilibrium constant is related to the energy change by a relation, and that relation is minus delta G it is equal to RT ln Kp. This equation suggests that for a spontaneous change, Kp value becomes very large, indicating that a reaction proceeds to a maximum extent in a forward reaction. Then Helmholtz free energy. It is represented by a symbol A and mathematically expressed as A it is equal to U minus Ts, where U it is the internal energy of the system and T it is the temperature of the system. S it is the entropy of the system. As entropy, temperature, and internal energy are state functions, Helmholtz free energy is also a state function. Then, for any chemical reaction, the total internal energy is not utilized to do useful work. Some part of this energy is lost to bring about the entropy change. And if ds is the entropy change, then the energy lost is given by here ds it is equal to dqr dq reversible. That means this q amount of heat absorbed reversibly at temperature T, and the small change in entropy, infinitesimally small change in entropy, it is given by ds it is equal to dq reversible by T. Therefore, dq reversible it is equal to the product of T into ds. If the energy in the above equation is subtracted from the total energy dE of the system, then the remaining energy will be useful to do work at constant temperature from the system. It is this energy which is called as Helmholtz free energy or work function. Then, for a process carried out at constant temperature, the maximum work done by the system is obtained at the expense of decrease in Helmholtz free energy or work function. Then, the relation between Gibbs free energy and Helmholtz free energy. Here, the relationship between Gibbs free energy and Helmholtz free energy. All of you know the Gibbs free energy is expressed as G it is equal to H minus Ts. For a system undergoing change at constant temperature, the free energy change is given by delta G it is equal to delta H minus T delta S, and let it is our expression number 1. Then the Helmholtz free energy Helmholtz free energy A is defined as A it is equal to U minus Ts. In your book, this internal energy it is denoted by letter capital E here. Then for the system undergoing change at constant temperature, the change in Helmholtz free energy is given as delta A it is equal to delta U minus T delta S, and let it is our expression number 2. But the enthalpy change for a chemical reaction at constant pressure is given by delta H, it is equal to delta E plus P delta V. Therefore, substituting this equation number 3 in equation number 1, we get delta G, it is equal to delta U plus P delta V minus T delta S. That is delta G, it is equal to delta U minus T delta S plus P dV. Since we have delta A, it is equal to delta U minus T delta S, and from the equation 2 we have this equation delta G, it is equal to delta A plus P delta V. And the significance of this equation is the delta G, that means free energy change in Gibbs function. It is the sum of Helmholtz free energy function plus P delta V. Here, the Gibbs free energy change differ from the Helmholtz free energy change by the work function, that is work of expansion, and this excludes this P delta V. This P delta V term is not included here. So, the Helmholtz free energy function, when it includes the term mechanical work, then we have the Gibbs free energy. And significance of Gibbs free energy. A chemical reaction is governed by three important thermodynamic functions. Here, enthalpy change, then entropy change, Gibbs free energy change. Then the above three functions are related by equation delta G, it is equal to delta H minus T delta S, and this equation has a great significance as it describes the spontaneity of a process. For a reaction to be spontaneous, the free energy change must be negative. However, the sign of free energy depends upon the sign of delta H and delta S. Hence, we can characterize the spontaneous process, non-spontaneous process. Okay. So, in this table, there is a characteristic of spontaneous and non-spontaneous processes. All of you know, for exothermic reaction, delta H is negative. Then for endothermic reaction, delta S value is positive and the delta G, it is a negative. So, all such reactions are spontaneous reactions. Remember, for spontaneous reactions at all temperatures, the delta G value is negative, delta S value is positive, and delta H value is negative. Then for non-spontaneous processes at all temperatures, here delta G value is positive for non-spontaneous process. Then entropy negative value, entropy decreases, and for endothermic reactions the value of delta H is positive value. Then the reaction is spontaneous at a low temperature. For such reactions at a low temperature, T delta S, it is less than delta H. Here entropy decreases and the value of delta H is negative, and the reaction is non-spontaneous at high temperature. That means at high temperature T it is equal to delta H by delta S. And for non-spontaneous process, remember at low temperature T delta S is less than delta H. Delta S value positive and delta H value negative. This table shows the criteria of spontaneity. Then we will see the next point tomorrow. Thank you. किती वेळाचं